To compute the correct price of a derivative product, one has to make a model of the future evolution of the underlying assets. By absence of arbitrage opportunities, these simulations have to be made in a risk-neutral world. Let's illustrate these concepts by computing the price of a European option. The option is referred to an asset whose initial price at time t0 is S0. The lifetime of the option is between t0 and t0 plus t. Finally, the payoff that defines the option is simply a function of the price of the asset at maturity. Since this is a European option, this payoff can only be exercised at maturity, so the payoff will also be at time t0 plus capital T. To price the option, we will write the price of the asset at time t0 plus t at maturity in the Black-Scholes model. So the price of the asset at t0 plus t is a function of a random variable. The random variable has a normal 0-1 distribution, and it's equal to S0, the initial price, times the exponential of R minus 1/2 sigma squared times t plus sigma square root of t times x. Notice that R is going to be the risk-free interest rate. This is the key to risk-neutral pricing. There's another parameter that characterizes the asset, which is the volatility. The price of the option in the Black-Scholes model is simply the expected value of the payoff at maturity times the discount factor. The expected value can be expressed as an integral of this product. This is the probability density function for the normal 0-1 distribution, and this is the payoff at maturity. The function used to price a European option takes the following arguments: S0, which is the initial price of the asset, R, which is the risk-free interest rate, T, which is the length of the interval during which the option is defined, sigma, which is the volatility that characterizes the asset, and finally the payoff, which is handled to the function that defines the payoff of the option. The first thing we do is compute the value of the underlying asset at expiry. For this we use the Black-Scholes model expression. Then we define the integrand. The integrand is simply the product of the norm PDF and the payoff of the option, which depends on the value of the underlying asset at expiry. Finally, we define the interval in which the quadrature will be made. This interval is between -10 and 10 because numerically this includes most of the probability of the normal 0-1 distribution. Finally, we have the pricing formula. We first define the discount factor, and the price is simply the integral between -10 and 10 of the integrand that defines the option times the discount factor.